Hi, this is Ana Doblas, and in this video we're gonna solve 5 multi-choice questions from the module 1. So the first multi-choice question, it's about the Snell law and the total internal reflection. So we have an interface between sunflower oil, so this is the oil, that has a refractive index of 1.46, and then here we have air, which we know that the refractive index of the air is 1. And we are illuminating the interface with a 45 degrees. And we need to know if we're gonna have total internal reflection, meaning that here what we're gonna have is a reflected beam. And we don't have any refraction, right? So we know that we have total internal reflection if the incident angle, which is gonna be 45 degrees, is higher than the critical angle. And if you remember, the critical angle is the incident angle such as the refracted beam, it's 90 degrees. So the critical angle is the inverse of the refractive index of the air divided the refractive index of the oil. So that critical angle is 43.23 degrees. So delta 1 or theta 1 is higher than the critical angle. So the answer is yes, we're gonna have the total internal reflection. The next problem is the multi-choice question number 3, and they told us that we have a 2 centimeter toy object that is located 30 centimeters in front of a concave mirror, which focal length is 20. And we need to know what are the features of the image. So this is the optical axis, and here you just need to forgive me a little because I'm not doing everything on a scale, but I will try to do my best. This is the concave mirror, right? And then here at 20 I have my focal length, and at 30 I have my object. So the first ray is the one that goes parallel, and then from here it passes through the focal length. The other ray is the one that goes through the focal. I wanted to change the color. The other ray is the one that passes through the focus, meet the mirror, and then go parallel to the optical axis. So as you can see, this is gonna be the image. So the image and if you remember on the mirror, we were saying that everything on the left is real and everything on the right side of the mirror surface is virtual. So the image, which is the intercept point, image is real, inverted, and higher and taller. So within the answers, the correct answer is image is real and taller. The next problem is problem number 6, with telling us that there is an optical system made of a thin convex lens of focal length f and a thin concave length of focal length minus f. So right there is telling us that the first is a converging and the second is a diverging, and it's separated by the distance f. So what we have here is, and they want us to know if the parallel rays remain parallel after emerging the system. So in other words, we need to estimate the, So we need to estimate the transfer matrix of the system, and we know that this is going to be a 2x2 matrix, and if C is equal to 0 means kind of like telecentric systems. So parallel rails remain parallel. So this is the system that they say that we have. We have here a convex lens, right? This is convex lens of focal length f. We have a free propagation of f. And then after the free propagation, we have a concave, which is a divergent concave lens. You see that I changed the age of the arrows to differentiate between converging and divergence. So my transfer function, and remember that when we are building the transfer function, we go from right to left. That's gonna be equal to my concave lens, focal length negative, and then I have my propagation at distance f, and finally I have my converging lens, my convex lens with a focal length f. So if we cannot see the matrix, this is gonna be 1, 0, 1 over f1. Remember that they are separated by a distance f, and the focal length of both lenses is the same. And then 1, 0 minus 1 over f1. So this is equal 1, 0, 1 over f1. And now the next product is gonna be 0f minus 1 over f1. And the final solution is 0f minus 1 over f2. And as you can see, C is minus 1 over f, so it's different than 0, so rays do not remain parallel. Do not remain. Let me see if I can type that one in a different. So C is equal minus 1 over f, so it's different than 0. So that means rays do not remain parallel. The solution from problem 10. So we have a 0-point-meter object that is placed 5 meters away from a concave mirror with a focal length of 2. And we need to know how far we need to place a 0.75 meter object, a second object, from a other mirror that they have the same focal length as the previous one, but now gonna have the same height of the image. So here what we're gonna work is we're gonna work with the imaging equation and then with the height. So we have a first mirror, so we have mirror 1 that we know that the focal length, and I'm just gonna call f because we have the same, is 2 meters. The height of the object is 0.5, and then the object is placed at 2 meters. No, sorry, 5 meters. So before I do that, we can work it out, the math, so we can put we're gonna pass the inverse of the distance of the object on the other side, 1 over f minus 1 over d sub 0. We can get common denominator to combine this. And now we do the inversion, so we know that the distance from the vertex of the mirror of the image, we can express it in terms of the focal length and the distance of the object. And now based on this, now the height of the image is gonna be f over d sub 0 minus f y sub 0. These are general equations. So this is gonna be image position, and this is gonna be image height. So we know that the image height for both the first and the second mirror are gonna be the same. So the second mirror, again, the focal length is the same, so just for avoiding notation, just gonna say 2. Now the height is a little taller, 0.75, and we need to estimate the location of the object. So that the condition is that the image of the second one needs to be equal to the image in the first mirror. So if we cannot work the math here, what we're gonna have is the focal length, the distance of the object in the second mirror minus f, and that's gonna be equal to, I'm sorry, and I forgot here, the height of the object in the second one. This is gonna be equal to the focal length, and here what we're gonna have is the position of the object in the first mirror, and now the height in the first mirror. So what we want to decouple is, this is our unknown, this right here it's our unknown, so we can put it on the other side. So we can say the position of the object in the second mirror, that's gonna be minus, I'm just gonna try to use the same color, minus f, that it's equal, so that goes to the right side, so the other thing goes to the left side, so that's gonna be d sub 0 minus f, and then the ratios of the height on the first one and the height on the second one. Now because you have that minus f, then your location is gonna be f plus d sub 0 1 minus f, and now here you have your ratio with the height. And if you plug up the values here, you're just gonna have here your 2 meters plus, now you have 0.75 over 0.5, and then you have 5 minus 2, and this is 6.5 meters. So your solution is gonna be B. The final multi-choice question that we're gonna solve in this video is the number 13. So they tell us that light travels through a new material at a speed of 1.97 multiplied 10 power 8 meters per second. And in this material, this is the material that we're gonna use to create a spherical lens, and we know that So we know that the refractive index of the lens, we don't know that, but we know that the velocity is 1.97 10 power 8 meters per second. They tell us that we have to reduce. The first one is 15 centimeters and the second one is 25 centimeters. And they tell us that the lens is embedded within olive oil. So we know that the refractive index of the surrounding media is going to be 1.47. And they're telling us how far we need to be how far from the lens we can observe a clear image located at the infinity. So just kind of like, I'm just gonna talk a little about this sentence, like where they are asking us how far from the lens we observe a clear image observed at the infinity. So when we think about lenses, right? So we have here a lens, and when we have an object placed at the infinity, that means that we're gonna see the clear image. All the rays are gonna focus on the focal plane, right? So this is gonna be defined by the focal length. So this is telling us a lot because we have the lens maker equation that we know that the focal length of a spherical lens is related with the refractive index of the lens and the surrounding media. And then we have here the radius. And we can try to work this one a little better. So we have here the difference of the refractive index, and here we have R1, R2 minus R1, and we can flip it over. So the focal length is gonna be the refractive index of the surrounding medium divided by the difference between the refractive index of the lens minus the refractive index of the media, and then we have the product of the radi divided the difference of them. And now we know exactly everything, right? So we have here the refractive index of the surrounding media is oil. We don't know the refractive index of the lens, but we know that the refractive index is C over B. So that is kind of 3 over 1.97. So that's 1.5228. This is the refractive index of the lens. And then radi 1 is going to be 0.15 meters. And then the second radius, that's going to be 0.25 meters. So when we plug all the values, we have here 10.4403 meters. So that means that the correct answer is the letter A for this multi-choice problem. So I hope that these videos help you to solve the rest of multi-choice questions so you can master Module 1 about geometrical and ray optics. Thank you.